Understanding scikit-learn's Nystroem kernel approximation. The Nystroem method is a technique for approximating a kernel matrix, which is often used in kernel methods like support vector machines (SVMs) or kernel principal component analysis (KPCA). It's particularly useful when dealing with large datasets where computing the full kernel matrix is computationally expensive. Here's a breakdown of the method and its implementation in scikit-learn. 1. The essence of kernel approximation. Kernel function. A kernel function measures the similarity between two data points. It's often represented as kx, y, where x and y are data points. Kernel matrix for a dataset of n data points. The kernel matrix K is an nxn matrix where the element key, J, is the kernel function applied to the ith and jth data points kxi, xj. Problem. Computing the full kernel matrix can be computationally very expensive, especially for large datasets. Solution. The Nystroem method approximates the full kernel matrix by using a smaller subset of data points called landmark points. 2. How Nystroem works. 1. Select landmarks. Randomly select m data points from the dataset Mn. These are the landmark points. 2. Compute the small kernel matrix. Compute the kernel matrix KMM for the landmark points. 3. Compute the cross-kernel matrix. Compute the kernel matrix KNM between the landmark points and the remaining NM data points. 4. Approximation. The Nystroem approximation of the full kernel matrix K is then computed as kprox KNMNP, Lena LG, InVKMM KNM, T. 3. Advantages of Nystroem approximation. Computational efficiency. The Nystroem method is significantly faster than computing the full kernel matrix, especially for large datasets. Memory efficiency. The approximation requires storing only the smaller KMM and KNM matrices, reducing memory footprint. Good accuracy. The approximation is often accurate enough for many machine learning tasks, especially when the number of landmark points is chosen appropriately. 4. Scikit-learn's implementation. Nystroem. The Nystroem class in sklearn kernel approximation implements the Nystroem method. Let's examine the key parameters. YAML. Key parameters for Nystroem. Kernel. Description specifies the kernel function to use. Defaults to RBF radial basis function. Options. Linear, poly, RBF, sigmoid, precomputed, callable. A custom kernel function. Gamma. Description. Kernel coefficient for RBF, poly, sigmoid kernels. Options. Float. Larger gamma means tighter clusters more sensitive to small differences. Auto attempts to automatically estimate gamma. Coa 0. Description. Independent term in polysigmoid kernels. Options. Float often set to 0. Degree. Description. Degree of the polynomial kernel. Options. Int default is 3. N components. Description. Number of components. Landmark points to use. Options. Int should be significantly smaller than the number of data points. Auto attempts to automatically estimate the optimal number of components. Random state. Description. Seed for the random number generator used for landmark point selection. Options. Int allows for reproducible results. None uses the default random number generator. Eigensolver. Description. Algorithm used to compute eigenvalues and eigenvectors of the kernel matrix. Options. RPAC uses ARPACK for fast eigendecomposition. LOBPCG uses LOBPCG for fast eigendecomposition with sparse matrices. Dense uses dense linear algebra routines. Full uses a full eigendecomposition of the kernel matrix. N jobs. Description: number of jobs to run in parallel for parallel computations. Options: int sets the number of CPU cores to use. None uses all available cores. 5. Usage example. Python. From sklearn, kernel approximation import Nystroem. From sklearn, datasets import load iris. Load the iris dataset. Iris load iris. X iris. Data. Initialize the Nystroem transformer. Transformer Nystroem components 100. Kernel RBF. Gamma 0.1. Fit the transformer to the data. Transformer. Fitx. Apply the Nystroem approximation to the data. X-transformed transformer. TransformX. Now, X-transformed contains the approximated kernel representations of the data points. 6. Choosing parameters. N components. This is a crucial parameter. Start with a smaller value and gradually increase it until the performance on your task plateaus. Kernel. Choose a kernel function that is appropriate for your data and task. Gamma for radial basis function kernels. Gamma controls the width of the Gaussian function. A smaller gamma leads to wider Gaussian functions, which can be more robust to noise and outliers. Eigensolver. Choose the appropriate solver based on the size and sparsity of your data. 7. Limitations. Approximation error. The Nystroem method introduces an approximation error. The accuracy of the approximation depends on the number of landmark points and the choice of kernel function. Choice of landmarks. The quality of the approximation can be sensitive to the selection of landmark points. Random selection is a common approach, but more sophisticated strategies are available. 8. Conclusion. The Nystroem method is a powerful tool for approximating kernel matrices, enabling the application of kernel methods to larger datasets. Understanding its inner workings and the key parameters helps you use this method effectively for your machine learning tasks.